Welcome back to Computational Genomics Lab. Today we are going to make heat maps, one of my favorite figures, which shows kind of how much your gene is changing by shades of color, similar to like a weather map. In fact, that like you can tell what the average temperature is on Earth, and red if it's hotter and blue if it's cooler. It'd be the same for a gene, saying across all these measurements, here's its average. Is it higher or lower than average in what samples? And so let's get started. I'm just showing you on the GitHub where we are again. In the masterclass lessons 07 visualization and figures, and we're making heat maps, and then we only have one more to go, and we're going to level up to level 8. We're going to start a TAC-seq. Okay, so heat maps, again, you can copy this into an R Markdown into your favorite version of RStudio. And I am here in 07. I'm going to make sure I set this as my working directory. Okay, good to go. So we are going to need a new package today, library HEATMAP. If you try and load this, it'll tell you what you need to install. In fact, I think at the top of your screen, it will tell you any packages you're missing from in here. I also have sourced our plot theme that we made earlier in our util folder. And again, a lot of logic here of what is going on with a heat map, things to think about. I suggest watching the videos to get a feel for it and then go back and see more detail. So I'm just loading our TPM results and DESeq2 results. These are really the only two things we've really needed the whole time. And we're going to do something different to our TPMs this time. So we have this TPM filtered object that we've been bringing in each time, and these are just TPMs that actually aren't all zeros, so that they're kind of been filtered, and we're calling that TPM filtered. So what we're going to do is log transform these. This is very common practice. It's very important. You can search more about log transform TPMs and find out all the details of why. But that's what we're going to need to do for our heat maps. We do not need to do that for the plots. There's just a few things you have to remember. Counts for heat maps, TPMs for bar plots. But we've done them the right way, and we will continue to. So we're going to do the log2 function on that TPM filtered, but each value is going to be have a 1 added to it. Again, there's lots more information on why to do that, but we're going to now call this log TPM matrix. Log2 TPM matrix. Where are you? Log TPM matrix. Okay, it's really just going to be the same thing, but the values are going to be very different than what they were in our TPM filtered. So if we look at TPM filtered, this first one is 70, and now if we look in our log2, that first one is 6. It's just a log transformation. Same relative values across all the rows because we did it to all the values in there. Okay, so what's really cool to do first is a distance calculation. That doesn't take up much space in the computer's memory, but really what we're going to say is how similar, if we take this column think of it as a vector, how similar is it to each other one, and how much is the second one similar to all the others, so on and so forth. And what we can get is like a family tree of how similar all the samples are. Okay, so let's do that, and it's just using this simple base R distance function, and it's going to basically take that whole column and say how similar are you to all the other columns as a whole, and a vector with each slot measured. So you can think of it as like a correlation between two very long rows in Excel or two very long columns in this case. And the method we're going to use to calculate that distance is Euclidean. You can use other ones. You can do question mark dist and find other methods, and I'll show you how to change the method in just a second. So we're going to make a distance matrix. So this has got 105 comparisons, the 15 columns versus each other, and how similar they are. And now clustering is what's going to give us the actual family tree looking object, and that's hclust here. You can check that out, and it also has its own method. And we're going to use complete so that all the samples are placed together. But you can also change that and look in the menu here. But Euclidean and complete are pretty straightforward. The only thing I would say to think about is if your matrix is ones and zeros, you might want to do a binary distance measurement, because that's different when there's only two values it could be, whereas in Euclidean it can be from 0 to 7, 20, 50. It's a wide continuous range of values. Okay, so we're going to do this HClust and make it an object. So we're going to do the clustering and then store it in this object called HCComplete. The complete is to say what type of method we used in the object. And you can see it's going to be kind of one of these crazy tables, but it's all of our data is in there to make that. And to make the thing, you just hit plot. That's a base R. We're not even using ggplot. Just plot HCComplete, and the labels are the column names of the log TPM matrix. This guy, so just these column names, which are the samples, and then a title and subtitle. So really nothing too tricky here. The main part of this is this, where we're taking this HCComplete, which is a function of the distances previously, then it organizes them by who's similar to who, and the labels that are going to pop out are the column names. Okay. Wow, cool. So we already have clustered all of our figure large. It's too large. Okay. So we have like what looks like a family tree, and so what we can see right away is the 24-hour replicate 3 time point looks a little bit off. So, you know, it should be right in here with its replicates. But what is nice is the 48-hour replicates look great. The 96 are all together. The 12 hours and the 0 hours are all together. And what you're really looking for is how different they really are. So this one's clearly very different than everybody else because it has a break right from the start. And then it's saying, okay, then think of these as 2 different parents having children, and then these are how related those children are, or however you want to think of it, but it's really just seq samples. And so we can say that, oh, wow, there's a big break right here. That's like quite large. So 24 and 48 hours are quite different than 96, 12, and 0. So we already have our result there by just looking at, like, of all the data we measured, how similar do they look to each other. And we can make however many clusters we want. I like what we just did because it's unsupervised and just raw data telling us what's going on. But we can use this function called cutTree. That's just base R. And we take that organization chart that is stored in our HCComplete, and we're going to say, okay, just make 5 groups for now because I have 5 time points. I think they should go that way. Again, it's not cheating, but you're manipulating the data to make sure there's 5 clusters, whereas before it just ended up that how it was. Okay, so then if we then do print clusters, what we find here is which cluster each sample is in. So we can see the 0 time points are in cluster 1, the 12 time points are in cluster 2, cluster 3 is all 24s, 48 is all 3s, 96 is in, oh, we have a weird 4 here. So the only one that's in cluster 4 is our wild type 24, which we saw, or a 24-hour time point, which we saw looked a little weird. At this point, you might think, I like to keep it because it shows the biological variability, but you could say, oh, this is a bad sample. I'm going to toss it out and redo most of my statistics, but then you're going to have to remove a replicate from all the other time points. It gets tricky, but you'll manage that based on whatever project you need in the future. But for now, we're just going to continue with all of these samples. Okay. So now we can make a dendrogram as well. It's really going to look very similar. And that's just using a different function in base R. So we have our HCComplete from above, and we're just going to add dend to it, which is a different way. We did HClust to get to that and then plot. But dendrogram is going to make it do really the same thing in the end, but just a different way to show you how to do it. And then instead of plot, we just do view, and we can see that this is way less fun. I think let's just stick with what we did before, HC complete, and then plot it and go from there. There was a reason I must have made this in here. Oh, we're going to take that dendrogram and reorder it so the clusters have to be in order. That's, again, not the most unsupervised way, and then we plot the same way we did for our one up here with the HC complete. This is just now saying dendrogram did the organization, and we're going to plot that, same labels, and it should look very similar. In fact, it does, but you can see the aesthetics are slightly different. We have a scale over here now, but we can also see that our, why are they so far down there? But this is our weird 24-hour time point, and a little more relationship of how similar the samples are. Same information, different function. Clustering is really an art. You can change things, so that's why I like that unsupervised thing that we did first, is it's just saying this is what the data told us to do. Okay, so we're going to make a heat map, and all we have to do is take our log TPM matrix, which just means we did the log transformation on our TPM filtered object, and we're going to cluster the rows, which are the genes, and the columns, which are the samples, which we just did. You'll see that clustering the columns is super fast because it only has to do a few comparisons, but if you have 20,000 genes, it's a lot of comparisons, and this is going to take 3 to 5 minutes. I'll fast forward through it, but for now I'll just explain what we're doing here. Is HEATMAP is the function, the new package we just loaded. What it needs is the data, and then do you want to cluster the rows? Yes. Do you want to cluster the columns? Yes. Do you want to scale the data, which is when I was talking about the heat map, that you want to say what's the average across all the samples, and then which samples is it higher or lower. So what you do is you go across the row, calculate the average, and then divide each value by that average, and then I'll tell you if you're above it or below it. You can look more into that if that still seems confusing. We do not want to show the row names for 20,000 genes. That'll just look like a big chunk of text that you can't read. But let's show the column names because those are our samples, and then a title for it. So that's all within the HEATMAP commonality, but really all you'd have to do is these three things. I would highly recommend scaling in HEATMAP and HEATMAP, but the P stands for pretty HEATMAP, and I think it is the best HEATMAP program out there in R because it is so simple. Its parameters are very simple and organized. Okay, I am going to, in the meantime, show you how we could have done a custom distance function here. So we're clustering the rows and the columns, but let's say we wanted to do a Manhattan distance or a ward distance, and you can just make a custom distance function here. So we're going to say function of x is simply that distance we did earlier of x, and the method is Manhattan, and now x in this case is going to be one of the columns we're going to calculate the distance for in our TPM log transform TPM values. Oh wow, that happened pretty fast. So let's take a look. It's a bit faster than usual. So we can see here that our 0 is in the middle here. Now this isn't our significant genes, this is just all genes, so in general we wouldn't expect that many to be changing. And we can see our 0 time point is here, 12 time points are here, so these genes aren't really changing. And then at 24 hours, these are starting to go blue, which means down. And where's 96? So at 96, these went down a lot more. These genes started going up. And this is all the relationship of each gene to each other. But again, this is a lot of data. We're going to make this more downscale for the significant genes. But really the thing that matters are these values up here, and it's somehow made our 24-hour time points come together. Here again, clustering is kind of wishy-washy, but it does give you the general relative differences between samples. Okay, cool. So we've made a heat map, And then if we wanted to change the distance function in pHeatmap, we can make our own version of that, where we're going to say use the distance metric Manhattan, call it custom distance, and then we're going to custom hclust here. We can make that, and then we can add these in here into our heat map, things that we did all the same here, changing the colors just to add some more functions in pHeatmap. And then the distance function, we can actually tell it what to do in pHeatmap as well. So this is a one-stop shop from raw data, or all your log transform TPMs, boom, right into a heat map. And so if we run and do that, it's going to take, again, a few minutes to run. But I think in the meantime, what we should do is just get down to our significant genes here and do the same. Really, we're going to do exactly the same thing. So we're going to take our log TPM matrix, index into the, now I regret running that heat map because this is pretty much going to look the same. We're going to take the row names of our log TPM matrix. So here, we're going to take all the genes, is what that's doing. And we're going to say take the ones that are in our unique sig genes object, which we have here, our 669 genes that are significant across time, and keep all the columns. So really this is just doing that same kind of reduction indexing into our sig genes. Let's make that. And then we can do the same distance function, but we're going to use a transmute here. Hold on to that thought. Our plot came up, and so what we can see here now is really the same exact result. There's probably some slightly different measurements in these distances because we did the custom distance function, but I just think it's really cool that you can tell it how you want to cluster and skip all those previous steps. But those previous steps are really nice if you just want to take a quick look at larger data frames and how similar each column is to each other. Okay, so we just made our sig log TPM matrix here, and we see it's 665 objects. These are just the gene IDs that were in our unique sig list and our TPM values, log2 TPM values there. That's why it's important to name these things with any transformation you've done. We'll calculate the distance. This t just flips things that way. So right now our data is across this way. Long computer science story, but in order to normalize, you need to turn them this way. And so that's all it's going to do is take the distance and for our sig genes, and we're going to use the method Euclidean, the same as we did above. We just didn't do the flip part, I believe, up above when we did the Euclidean. And so, yeah, we just did. Oh, we did. Okay. So, just know that you have to do that. You have to take the column and turn it sideways, basically. So you're actually going to take all the values of that column, turn it into a row, do the comparisons, and then it will give you those distance comparisons in that funky type of table we looked at. So just remember, you have to do that T to do the clustering and getting the distance. And so we're going to do that for just our sig genes now, and then we're going to cluster them. You could use dendrogram. I prefer to use cluster, and we're doing this all kind of manually. All of this could be done in pHeatmap again, and then let's plot it. We're plotting the same thing. We're just using this different object, HC sig gene distance matrix, and that should run much faster. And so what we can see now, if we just look at our significant genes, we see kind of a similar pattern, 96 together, 0 together, 12. Our 24 is out there, but not quite as far out there with respect to just our sig genes. And I think this is a fair way to say it. I just want to take the genes that were statistically significant by changing in DE-seq, p-value, and log-fold change, and do a heat map on those. Again, you can do this custom function here and we'll plug it into our P heat map, which I just love. I've mentioned, I think it has all the parameters you really need, but I want you to know the fundamentals that are going on, that you can do this on your own and make these plots without P heat map in case P heat map ever disappears. And so we're just taking that significant log, just our significant genes that have been log transformed, and we made a heat map, and now we can see some of the differences here. So the 0 time point, we see these genes are on, then they go down. They were on at 12, so 0 and 12 they were on, and then in 24, 48, and 96 they turned blue, which means they went down. We could order this at this point to force it to be in the right order. Makes it a little easier to read, but we can clearly see that at 0, these are red at 12, and then 24 and 48 is when they go back down. And that's what we've been seeing, is that at 24 and 48 hours, most things are starting to happen. So now our scale is from log fold 2 of 3 to -3. Let's change that to 2 to 2. So we can make a breaks like we've done with histogram, and we're going to say, give me the sequence of steps. Seq is going to give you all the steps in between -2 and 2, and I want 51 steps is all this is saying. Okay, so we just are changing the scale of this heat map, and then when we say we should add our breaks in here. Yeah, breaks is equal to breaks. So now instead of P heat map deciding the log fold changes and everything, we're setting it to what we just made here. Cool. And let's take a look at that. Looks a lot better. Look at all that red. Okay, so now we can see that 0, 12, it's the same data. We've just shrunken the scale here. But it's always really important to show your scale in a heat map, because you could fudge and make this 0.5, and it's going to look super intensely different, but it's really just a small scale. Okay, so now this heat map was made with TPMs. You can do the exact same thing for R log counts, which we made way back in the DEseq lecture, but they're saved in your 06 folder results DDS time point long data, our data object we made. I'm just going to load that. Typically you would want to do heat maps in count space or rlog count space. You've been using the counts tables, and you can play with that. This is just going to rlog those counts. Don't we already have rlog counts? No, so we're just going to run the rlog function from DEseq2 on our DDS object that I don't have DEseq loaded. So it's not going to do that. Okay. Now it's calculating, and it's normalizing low data points that tend to be quite random when there's very low count information, and smoothing that into more of a straight line for the things not to be skewed by low values. And then this is that assay function from DEseq, if you remember way back when, and that's just to pull out the information. It just did the calculations in its memory, and now we're pulling it out with assay, and we're calling it R log counts for our mouse long time course. Now we're just going to index and get our sig genes. So we're taking that object, the row names that are in unique sig genes, those are the rows we want, columns, same as above. We're just doing it on this rlog counts table, and we're using the same breaks we just made and plotting it with counts in P heat map. And let's see if it looks different. Okay, it actually does look, I mean, it's ordered differently, but now our red at 0 and 12 is here, and we can see it going to blue in the 48 and 96. So you're getting roughly similar results, but I think I, in general, would use rlog counts because of that extra normalization. It just is a little cleaner. And so I think we should just leave it there, because this is just reordering things, and we don't really need to do that, but if you want to keep going here after line 200, what it's doing is just simply ordering these in the actual time points. Again, it's not cheating, but makes it a little easier if you were to make a figure. But let's save all of our data. And really all we're saving is our rlog counts matrix long time course, that rlog function we just did. We're saving in our results folder. Let's see where we are. If we go to working directory, we are in the right working directory, so we can save this here. I don't think we need readr, but nope. Okay, so then we wrote out our long RDS, so we can reload that in the future. But congratulations, you've made a heat map, and there's a little more material here if you want to see how you can order your samples so they're in the right order. That's here, be a fun exercise. And then I have other fun exercises here that you can do to make really cool heat maps, different styles, magma. You can play around and see what you like. Okay, next is plotting raw data in the genome browser. This is so cool. You get to see your data in the genomic space and where things are. So congratulations on making heat maps, and we'll see you next time.